Okay, hello everyone. This is the 27th lecture and the last one in this course. And I really want to thank you now, and I'll do it again at the end for still being here. So we've been discussing the first law of black hole thermodynamics, and we're just going to continue discussing it from slightly different point of view from last time. So last time we actually defined these Komar integrals. We didn't use them. And we also calculated the first law, or what looks like a first law, using the Kerr-Newman solution. So we had a specific black hole. And as you know, this solution has a mass, an angular momentum, and a charge. And we didn't define, we actually calculated using the data of this thing, that dm is kappa dA upon 8 pi, where kappa is the surface gravity, plus omega dj plus phi dq. And this is what we call the first law. And the only thing is it's not that general because we use the Kerr-Newman solution. Now, of course, the Kerr-Newman solution is very general in the sense that if you have a vacuum solution, essentially it's the most general under if it's going to be stationary. And yet we want to do something better today, which is to say we want to consider generic black holes about which we only know that they are stationary. And of course, it will imply the result of yesterday, but it can be more useful because we can have situations where a black hole is not stationary initially and there is matter maybe falling into it, and later in time it becomes stationary. So somehow we want to use this asymptotically stationary property and see where we can go with it. Now, for this, there's a very important theorem which we've already discussed, though we never really proved it because the proof is quite tedious even by the standards of this course, which basically says, or let me say it precisely, asymptotically flat space-time plus stationary. And there's one more assumption which is called analytic, which means that given Cauchy data on the initial slice, the evolution is an analytic function of that data. Given all these things, we get two outputs. One, the event horizon is a Killing horizon, which means that it's null hypersurface which is ruled by a Killing vector. And as we know now, when there's a Killing horizon, there's also a surface gravity, which is the amount of non-affinity of that Killing vector. And the second result is that the solution is axisymmetric. It could be more than axisymmetric. It could be spherically symmetric, but it's at least axisymmetric. Now, we are really interested in the second outcome because it's going to actually help us prove the first law. And that's not surprising because the first law has J in it, dJ. So there should be an angular momentum. And well, we'll see that we can derive it, assuming the result of this theorem. Now, as far as the proof of the theorem, I did sketch it in a few lectures ago, but it's too complicated to go into in detail. But there are two key steps. And one of them I'll summarize, and the other one I'll use to get a formula, which we actually need. So the first step is, let's have a look at this. So we assume there is a bifurcate horizon. This is part of the saying that it's analytic. So if it's analytic, then it can be extended across the original horizon into the other regions 2, 3, 4, and then we get a bifurcate horizon. And then this thing is the bifurcation surface. And we have these two null hypersurfaces. Now, Hawking observes that let's consider so he asks, let's consider the solution of the Cauchy problem in a neighborhood of this bifurcation surface. So because of analyticity, if we give Cauchy data on the horizons, we'll get a unique solution in that neighborhood. And once it's, since it's analytic, it's actually determined everywhere. Now, by varying this Cauchy data, he shows that there is actually a variation which has the effect of moving points on this killing horizon in this direction, namely the ones to the future of it move away from it that way, and the ones to the past also move away from it that way. However, at the same time, the points on this other killing horizon move exactly the other way, namely both sides, from both sides, they move towards the bifurcation surface. Okay, so he finds a particular transformation of the Cauchy data which has this effect. But if that's the effect which preserves the bifurcation surface and the individual horizons, it just moves the points, but the manifold, which is each horizon, isn't changed, then it implies that there must be a killing vector doing this job. And doing this job, carrying out this motion of points, and we'll call it K prime mu, because we have another killing vector coming up. And K prime is null, so K prime squared is 0, because it is a null generator of each branch of this bifurcate horizon. So this alone proves part 1, because it implies that these horizons are killing horizons, because all we need for a killing horizon is to have a null killing vector which rules it. Okay. So this is 1, and I haven't given you any good reasoning. I'll try to give you a better reasoning for 2. So this is 1, proof of 1. For 2, we want to show axisymmetry. And now we bring in another killing vector, because in the assumptions, there's a assumption of stationary, and stationary spacetime is one which has a killing vector everywhere, but which is time-like at infinity. Okay. Usually stated as being time-like at null infinity, but by continuity, you can also bring it to I0, and it will still be time-like there. Once it's brought away from infinity into the bulk, it need not be time-like. It could turn null, it could turn space-like, and as we'll see, both of these things actually do happen. Okay, so this killing vector I'm going to call K mu. So I have 2. And the first question I want to ask is, can K mu be the same or just proportional to K mu prime? Is there only one killing vector rather than 2? And if you go back and recall the Schwarzschild solution, actually K and K prime are the same, because what happens in Schwarzschild is that you have this crossed structure, and here you have something that's time-like. This is K. And as we've seen in suitable coordinates, where you can actually extend it all the way to the horizon and beyond, it starts to bend like this. And by the time it's on the horizon, it's actually pointing along the horizon. So in fact, it's null. So the same guy, which is time-like at infinity, is null on the horizon, and that's just one killing vector. But this isn't what happens in general. It's a consequence of spherical symmetry. You can check in any other black hole solution that's not spherically symmetric. that this isn't what happens. So let's ask what does happen. So in general, how does K look on the horizon? So remember, K prime is the one that's already null on the horizon, and we don't care what it does elsewhere because it's just the statement that that it's a killing horizon. But K is the one that's time-like at infinity. We want to ask how it looks on the horizon. And let's look at the possibilities. So let's examine the horizon a little more carefully. Let this be the future event horizon H plus. So we ignore the rest of those things. Just let's focus on this line. First of all, this isn't a line because at every point there's a sphere. And this is what we call the horizon at a fixed time, which is the one whose area we evaluate. So this sphere is parameterized by the angles theta and phi. I'm in 4D. And this horizon has a affine parameter u that runs along it. And there's another, or better, I can say that this has the killing vector k prime, which I just defined, which runs along it. Okay. Now, there's going to be an orthogonal direction like that. Okay, orthogonal as usual is a bad word. There's going to be an independent null direction n mu, which actually goes in from the horizon, right? That makes up all the four directions. The one generated by k prime, which is a killing vector, the one generated by n, which is independent null vector, but not necessarily killing, and then the ones generated by motion of theta and phi, which are again not necessarily killing because we are not assuming spherical symmetry. So these are the four coordinates. Now, where does K point in this picture? So we bring it in from infinity and we ask where it can point. So the first question is, does it have a component along n mu, this one? This is n. So can it have a component along n mu? And the answer is no. And you could try to guess why that should be the answer. Because look, this k, whatever it is, space-like or time-like or anything, it's still a killing vector. That means it's a symmetry of the space-time. It's an isometry. And if an isometry acts in that direction, then it's going to deform the horizon. The horizon will go somewhere from r equals 2gm or whatever the horizon is in a general black hole. It'll go in or out. But you're not supposed to change the horizon because if you do, then that can't be a symmetry. Symmetry has to preserve the horizon. Okay. So because of that, there's no way that this can point uh, away from the horizon. It has to therefore K is tangent to the horizon. Now, this horizon, I think I mentioned once that sometimes we use horizon for a 3D null surface and sometimes for a 2D space-like surface. So here we mean the 3D null surface. So that means its options are any of these. Either it can point this way, or it can point along theta or along phi, or most generally it can point along all three of them. Okay. If it points directly along K prime, then it is basically equal to K prime. Then it's null and proportional to K prime. And all that will happen if in that case is maybe you change the parameterization, but it's the same basic vector. And this is the spherically symmetric case we already saw. And this is very special. This means that the vector actually has no components along theta and phi in this picture. Along theta and phi. And that's exactly a consequence of spherical symmetry. But in general, it will. So in general, K prime is space-like. So it's both tangent to the horizon and space-like. Okay, because even if it has a component along this direction and some components along these directions, the net result will be to make it space-like. So it's space-like. So now we have one null killing vector k mu prime and one space-like killing vector k mu on the horizon. Okay. So any vector that's tangent to the both of these are killing vectors. So any linear combination of them will be a killing vector. So any linear combination A k mu plus B with constant coefficients is also a killing vector. Okay, so far I hope everybody is with me. Okay, now what we are going to do is to look at all such linear combinations and find A and B such that this linear combination A k mu plus B k prime mu has closed orbits. So what is the geometrical picture? In general, if I have a vector that's a that's tangent to the horizon and linear combination of the null direction that way and also the directions that go around the horizon that go round on the horizon, then the general linear combination can do something like this. Can generate a motion which is partly around the horizon surface or off the horizon surface and partly translating along the null generator. Okay, then its orbit is enclosed. Clearly, this thing is enclosed. But now from this thing, if I subtract this thing by an appropriate amount, then I'll remove that helical motion in that direction, and now it will only act like this, and its orbit will be closed. So I hope the intuition is clear there. So there must be a linear combination, this is Hawking's argument, of these two vectors which has closed orbits, and we'll call it W. And now we are actually done because this is the killing vector of axisymmetry. Because the mere fact of having a closed orbit at the horizon means that this killing vector is generating a motion which goes around an axis. It means that the coordinate conjugate to this vector is an angle. It's angle valued. In fact, can be taken to go from 0 to 2 pi. And an angle determines an axis. So we have an axisymmetric black hole. So it's as simple as that. So just the fact that you have one space-like and one null vector, and you're allowed to take linear combinations, gives you this W, which is the axial killing vector. So this is a very nice result, and we can slightly improve it by noticing the following. Normalization of K is fixed. Okay. Norm of K is fixed because it's the one which was time-like at infinity. So we just could have taken it k squared equals -1 at infinity. And once we do that, it's normalized everywhere. Okay. But the normalization of k prime is not fixed. Why? Because it's null. Very familiar problem. And because it's null and we defined it by its behavior on the horizon, we don't actually even care what it does away from the horizon. Since the normalization of k prime is not fixed, we can change it. And by changing it, we can bring this equation into the form W mu equals A k mu minus k prime mu. Okay. Yeah. Let me just check that I'm doing things right. K prime minus k. No, I want k prime minus k. So I should have started here with this. We'll take a k prime plus b k And here we'll write this. So we basically, what we've done is made A and B, well, you could call this B. Let's see, what did I do? So I changed the normalization of K prime. So this actually B, mm, mm. So I can call this minus B. Yeah, this is correct. I simply made A equal to minus B. Okay. And so by changing the norm of K prime. B is still arbitrary. So the original linear combination had two arbitrary parameters. By normalizing K prime, I came down to one arbitrary parameter, which I can't remove. Okay. And so I can write K prime mu equals K mu minus 1 by B W. Now you might think I can remove B by absorbing it in W, but I can't because W has been normalized so that its orbit has a length 2 pi. If I absorb B in it, the orbit length will change. I'm free to do that. It's a very familiar story we all know from circles. You can choose the angle to be 2 pi anything, but your formulae simply all change. So it's best to take it 2 pi. Okay. And now we are going to define this constant to be omega h, and we'll call it the angular velocity of the horizon. And as often with formulae like this in GR, the interpretation is actually solidified by computing it in a particular metric like curve and finding that it's actually the angular velocity of curve, which is a fixed function of the parameters. So at the end, we get K prime is equal to K plus omega horizon W. This is an important equation and we are going to use it in a moment. One reason you can see why we would want to use it is that we've already talked about Komar integrals yesterday, and I'll review it briefly again today. And in the Komar integrals, K, the one which is, K is used to define the Komar mass, and this guy is used to define the Komar angular momentum. So we've actually got an interesting relation and we are going to exploit that. In fact, I'm going to use this in the form trivial change. Just I'll solve for K. So K is K prime minus omega W. Okay. So this is an output of Hawking's theorem on generic asymptotically flat stationary spacetimes, and because they are proved to be axisymmetric, W does exist, and this is the relation between the killing horizon vector, which is this one, the axisymmetric vector, which is that one, and the time-like vector making it stationary, which is time-like at infinity, which is that one. Any questions on this?
So can you please recall how this W was shown to have closed orbits?
No, so I didn't say that I can, I said there must be a linear combination which has closed orbits. I didn't show that it has closed orbits. So the point is that by taking a linear combination of these two vectors, you keep changing the orbit, right? This vector, let's see the orbit of this. This is along the null direction of the horizon. This is unknown because we brought this vector from infinity where it's time-like, but now we don't know what it does on the horizon, but it's tangent. Okay, so given two tangents to the horizon which are linearly independent, I should be able to make one linear combination which has closed orbits. So there might be a more rigorous proof, but it's pretty intuitive because of the picture I just drew about the spiraling. So my point was that a generic vector tangent to the horizon can have a component along k, in which case it will obviously go along the horizon as it winds. When its components along theta and phi will make it wind, in particular phi. Okay. But actually, I think it doesn't matter because at this stage we don't even know what is theta and phi, and this isn't a round two sphere. This is just a topological two sphere. So, right, in fact, for Kerr and for any metric that's not Schwarzschild, this is not a round two sphere with the precise metric d omega 2 squared. Okay, but its angles generically I can call theta and phi or theta 1 and theta 2. So if it's not, if k is not purely null, then it certainly has a component along a compact direction. Okay, and also it's important here that this should be topologically a sphere and not say a torus. Okay, so in a sphere, if you are going along a compact direction, is going to, I mean, yeah, it's just, I think it's just intuitive that there will be some compact, there'll be some way to coordinatize that thing so that the compact direction is just a closed orbit around it. And what you do using K prime is to eliminate the part which makes the orbit go that way. It's just an intuitive proof. But if you want a more precise proof, statement and proof, maybe you should look at Hawking's paper. It's the one called black holes in general relativity. It's actually before the laws of thermodynamics paper of Bardeen, Carter, and Hawking, a year before that. Okay?
Yes. So my confusion was like in the case where uh, the horizon may not be a sphere at each point,
It
even
topologically has to be.
topologically.
That's yeah, yeah. Okay. Okay. So in
So
that case, you're saying it's not obvious that there is any combination which has a closed orbit.
yes, that because there may not be a compact direction.
No, theta and phi are compact directions by definition. The fact that it's a sphere means it has two independent, both compact directions. They're not
No, no,
independent in
no.
the sense the metric mixes them, but there are two directions and both are compact in the sense that the angles, however you parameterize it, the angles have to have compact values.
Uh, yes, but then does that follow from the assumptions that I mean this horizon at each point uh,
Ah,
being a compact at each point, does that
uh,
follow from this asymptotic flatness, stationarity, and so on?
Yeah, good question. I think so there is a proof that the horizon in four, so this is now actually a 4D thing. The horizon in 4D is always a sphere. This is not the case in say 5D where you can have black rings and then in higher D where you can have various shapes. But in 4D, certainly it is proved that the horizon has the topology of a sphere. But if we assume that, you still have a question that whether we can find a closed orbit?
Uh, no, no. In case it is compact, then I'm fine. Then we
Ah,
can certainly
yeah,
find.
yeah. I think this we know. I think this is provable. Well, first of all, yeah. Okay, I don't know the proof offhand, but I believe there's a proof, and probably Hawking refers to it in his paper because I think that's part of showing that there's a closed or a compact a closed orbit.
Mhm.
The,
Yes, thank
the,
you.
the observation is simply that, so what really makes the orbit not closed is not the presence of the sphere, but the presence of the null direction like that, which, as I showed, can allow you to never close your orbit. So given that K prime is available, it can just be subtracted in this way, and then it gives you a closed orbit.
Yes, thank you.
Okay. Okay, so now armed with this information, we are going to go back to the first law. And let me recall its form, that the form was dm equals kappa dA over 8 pi g plus omega dot dj plus phi q dq. So this is the proposed form. Okay. Now, before I go on to the more general proof that doesn't start with the Kerr-Newman metric, let me just comment, which I said already yesterday, that it's not possible to uniquely identify kappa with temperature and area with entropy, because there's a arbitrary factor, and let me write it this way. Let's write kappa is alpha times t and a is 8 pi g over alpha times s. Then this implies that kappa dA upon 8 pi g is TdS. And that's what you want the entropy law, the entropy term in the first law to be. So this leaves alpha undetermined, and it remained undetermined. It's very important that both in Bekenstein's work and in the work of Bardeen, Carter, and Hawking, which were roughly at the same time, 72, 73, this parameter alpha remained undetermined. I'll encourage you to read Bekenstein's paper, where he has some interesting ideas about how to determine it. He certainly tries, and he uses some notions of classical, some kind of classical notions of entropy, of information rather, classical notions of information. Now we know that quantum information may be more relevant, but at the time he was using some classical probabilities, and he even gave some formula for alpha, but that turns out to be wrong. And it was 2 years later, 1975, when Hawking showed basically, so one line summary of Hawking's paper, particle creation by black holes, is this, he simply showed that T, rather, the temperature of a black hole is h bar kappa over 2 pi. So this, if you like, everything comes from this formula of Hawking. If T, so he basically, alpha is therefore fixed to be h bar over 2 pi. For some reason I have done, no, alpha is fixed to be, sorry, alpha is the other way. Alpha equals 2 pi by h. Okay, the presence of h bar in this formula clearly says something quantum is happening, but it's not gravity that's quantum. He didn't quantize gravity. It's just from a study of quantum effects of fields that exist outside the black hole. Okay, so just from the existence of quantum field theory, not of gravity but of some other matter, we get this h bar and 2 pi, and it's all calculable and calculated. And this immediately also tells me that I know the relation between entropy and area, because S is alpha upon 8 pi g area, that was known earlier, and now alpha is this thing. So this is equal now to A upon 4 g h bar. And this is what is now called Bekenstein-Hawking entropy. Bekenstein's contribution was to identify A up to a constant with entropy and to try and guess that constant. Bardeen, Carter, and Hawking at the same time also came to the same identification independently, but also couldn't identify the constant. And then Hawking alone, 2 years later, got the constant. And once it's fixed in the temperature, it's fixed in the entropy, because the product has to obey the first law. At least that's what we would like to, that's what we need for this interpretation of area being entropy and surface gravity being temperature. So this sort of concludes the first law statement. And now let me finally turn to the derivation of first law. Now, every derivation has some limitations, but this one I find particularly transparent, and is going to use Komar integrals. They will define for me both so Komar integrals and Killing vectors. Therefore, this is all going to work for stationary spacetimes. And we're going to use both the Killing vectors k and k prime and their linear combination w, which we've already introduced. Okay. So now let's recall the Komar integrals. The mass integral was minus 1 by 8 pi g, limit r goes to infinity, integral d sigma star of d k. K is the same notation. It's the time like at infinity Killing vector. And the Komar angular momentum, on the other hand, is 1 over 16 pi j, same limit, integral over the same, this is the boundary of sigma. Star d w, where w is the axial Killing vector. Good. Now let's make a comment about sigma. What was sigma? So sigma was essentially a Cauchy hypersurface, but in general we chose it to be a space-like hypersurface. And in the original quote derivation or motivation due to Real, we started with a bulk integral of that current which I call J prime, and then we went to the boundary. And you may ask the question that how do I know that the boundary of my space-time is only this region r going to infinity? For example, if my space-time is the exterior of a black hole, then it has another boundary on the black hole horizon, and I didn't account for that. And the reasoning is that here I was working with something more like a maximally extended space-time, and with this kind of structure asymptotically, and a Cauchy surface. And so these were two copies of I0. And the Cauchy surface basically it could go this way also, but it ends at I0. So this is sigma. So one of these I can pick to be sigma, doesn't matter which one. And in that case, the boundary of the region of sigma is the boundary at its ends. Okay, so boundaries at space like infinity. Boundary del sigma. Okay, so this is why I transformed a bulk integral into a boundary integral at I0. But now I'm going to apply the Komar formula to a slightly different situation, which is one where I have a single-sided black hole, which looks more like just this part of the space-time. And this thing here is the horizon. Okay, I0 is here. And now I'm going to choose a Cauchy surface which starts at I0 like before, but it ends over here on the horizon at any point. This is sigma. And we are now going to do calculations for this sigma. So what's the difference? Well, in this case, sigma is a Cauchy surface only for the exterior of the black hole. And because we are defining these things in the exterior, we'll be able to extract properties of the black hole. Okay. The point is, if I keep account of the matter outside and the change of the black hole, then intuitively I would expect that when matter falls into a black hole through the horizon like this, the entropy outside will decrease and the entropy inside will increase. Okay. And it's the entropy of the inside which is captured by this area which is increasing. But we only want to look at the entropy of the black hole, the contribution of that. Because finally, the first law we are trying to derive is not a first law for the whole world. This is the first law, you could call this the black hole contribution. It's the first law of black hole thermodynamics. If we merge black holes with all the rest of physics, then of course all the contributions from rest of physics have to be added to it. So we want to isolate those. And the way to do that is to pick the Cauchy surface sigma to be like this, ending on the black hole. Now, where does it end? Well, it ends at a point on this line, but of course, this point is again a two-sphere topologically, the same one we've been talking about. And it's what we call the horizon when we mean the spatial horizon. This is not a null surface, it's just a two-dimensional space-like surface with the topology of a sphere. Okay, since it's ending at a point with respect to the null direction, its only directions of this point are the two directions along the sphere. Okay. Now with this choice, I start with the definition mk on the boundary of sigma at infinity. So because remember the definition we settled on was the one where where did I write it? Sorry. Oh, here. The definition we settled on was this one with the limit r goes to infinity. Okay. And now we are going to, so we are here, and we are going to do the inverse of Stokes' law. So we'll map the mk, the Komar mass, onto a bulk contribution plus a contribution from here. Remember, the bulk contribution is on sigma. Everything is on sigma. We have a surface integral here. It will be mapped to a bulk contribution all along sigma and another surface contribution on the horizon of the black hole. And the formula is very straightforward. We simply have mk is equal to the bulk Komar integral, which we discussed yesterday, rewriting it now not in differential form. So this is d3x, and this is on sigma. And then there's an extra term minus 1 over 8 pi g integral on h star of dk. So star of dk integral, that was the surface term we started with. Now it's also the surface term we end with, but it's on evaluated on h. And then there's this contribution. So far, so good. Okay. Now let's work on this contribution and rewrite it. We want to have an expression for k in term. Now remember, now this k, this is our time-like killing vector, which was at infinity. But because of this procedure, it has now been brought on to h. So it's exactly the vector we discussed about 15 minutes ago, which is the vector tangent to the black hole horizon when we brought it from infinity where it was time-like. And generically, it's now going to be the space-like vector tangent to the horizon. And it satisfies, so we already derived this equation, that k mu is k prime mu minus omega h w mu, where this is the axial killing vector and this is the null killing vector, all on the horizon. So everybody is on the horizon in this equation. And now I can just take d of everybody here, and then I can put a star on everybody. Let's move omega out of the way. Put a star here and integrate over the horizon. Okay. So this now, okay, not this. We won't discuss this first. Sorry, excuse me. Okay, what's the next step? Well, the first step actually is that this last integral is easy. This is the Komar integral of the axial killing vector on the horizon. So I can reasonably call it the angular momentum of the horizon. And this omega also should be called the angular velocity of the horizon. Okay, I don't know, was I using curly h or regular h earlier? I don't even remember, but it hardly matters. Anyway, it doesn't matter. I'm going to drop these h's. So this term is minus omega h. Oh, sorry, there's a 16 because the Komar integral jh had a 1 over 16 pi g. So this factor is there and the minus is still there. Okay, good. Now we have to argue good. So now exactly. So in this formula, This one term I'm leaving alone. I'll take it along. And it's only this term I need to rewrite. And I've rewritten it by eliminating this in favor of this and this. And I've rewritten one term of this. Okay. So now we have to work on the null killing vector and rewrite its integral on the horizon. The integral of star d k prime. Okay. So claim, and we're going to prove it, and it's the only tedious part. The claim is that if I integrate on the horizon star d k prime mu, I get minus 2 kappa a, the surface gravity times the area of the horizon. The surface gravity, if you remember, is defined by the geodesic equation for k prime. K prime is a non-affinely parameterized geodesic. So we have k prime mu del mu k nu is equal to kappa k nu. So this defines kappa. And A is defined by just integral h of 1. It's just the integral of 1, of course, means root det g. The projection of the metric, whatever it might be, on the horizon. So there'll be a two-dimensional metric on the horizon, and when we integrate it, whatever we get is A. Okay. And we'll find a nice way to write this integral and to prove this result. So let's get down to that. So the left side of this, so yesterday I made a big deal about writing everything in differential forms. But it turns out that it's easiest to manipulate these. Oh, sorry, there shouldn't have been a mu over here. It's d of a 1 form. So this k prime was a 1 form. Its index was suppressed. Taking d made it a 2 form. Taking star made it a dual 2 form in 4 dimensions. That's the 2 form integrated on the horizon. Okay. So the LHS integrand star dk prime in components is, and I already said this, I think, yesterday, epsilon mu nu alpha beta del alpha k prime beta. You can see it because the act of taking d over here is this. You may say that d is an ordinary derivative, but actually in this line there is only an ordinary derivative because these two indices antisymmetrize this, and or equivalently killing equation antisymmetrizes this, and so the connection part in d doesn't contribute, but we can take it along anyway, just so that our equations look covariant. Okay, so this is the quantity. Now, a very simple theorem. So this is a 2 form, obviously, and we are integrating it on a 2 surface. Now, any 2 form, A mu nu on a 2 surface is proportional to epsilon mu nu. Now, epsilon mu nu, of course, we are familiar that in a normal 2D surface, it's just the guy that epsilon 1, 2 is plus 1 and epsilon 2, 1 is minus 1, is the 2D version of the more familiar 3D or 4D epsilon symbols. But in gravity, these always come with a root det g factor so that they can be proper tensors. And this is the tensor which is actually integrated on the manifold. So then there's no reason to write root g either. You can just write that epsilon is integrated. So A mu nu must be proportional to epsilon mu nu. And I'm going to put a 2 here so that just to highlight that it's a 2-dimensional thing. And the proportionality factor I'll just call A. This is a function. Okay, both are functions. This has to be so. This is, a familiar statement that if I have a second rank tensor in 2D space, then it has to be proportional to epsilon ij. Okay. And so there's only one function which determines it, and that's A. Now, we can act with the epsilon upper mu nu on both sides. So we get A epsilon mu nu, epsilon mu nu. And this thing is 2. And therefore, A is equal to half epsilon mu nu, A mu nu. Okay. So we are going to use this to integrate this 2 form. So how are we going to do it? Well, we have to take this 2 form and think of it as A mu nu, this A mu nu. And then we have to dot it with epsilon mu nu, which is the 2 form on the horizon. So we first need to figure out what is epsilon mu nu. And the way to figure that out is not very difficult. Again, let's remember that the horizon has a direction k prime here and a direction n here, and then 2 space-like directions, which are the ones we want to capture, which we are calling the horizon. And therefore, the claim is that epsilon mu nu 2 is simply epsilon mu nu rho sigma n rho k prime sigma. So basically, the n direction gets taken away. So this rho is along the n direction, this sigma is along the k prime direction. Whatever is left has to be along the theta and phi direction. And this whole thing is a completely tensorial expression, so it has to be the right one. The only question you may ask is, well, what about the normalization of n and k prime, both of which are null and therefore neither of which can be normalized? Well, they can be normalized together, which is all that really counts. So we choose n mu k prime mu equals -1. So that doesn't normalize each one, but it normalizes the product, and that's good enough for this equation. So, sorry. Oops, I keep doing this. This equation is well defined with this normalization. Okay. So now I need to calculate this quantity, scalar quantity A, as half epsilon mu nu. So first I need to calculate epsilon mu nu, A mu nu, where epsilon mu nu is, so epsilon mu nu, A mu nu is equal to epsilon upper mu nu lower rho sigma n rho k prime sigma times A mu nu, which is epsilon mu nu alpha beta gradient alpha k prime beta. So that's the product I want to calculate. Okay. Now we have 2 indices contracted. Okay. And I'm a little struggling with the minus sign, but I think the minus sign comes from the fact that so first of all, you know what happens when I take an epsilon and another epsilon. However many indices are contracted, I get that number factorial. So that will be 2. And then I get delta functions which equate rho with alpha, sigma with beta, and then minus the opposite. Okay, not delta because now here both are lowered, so I get g's. So I'm going to get something like g rho alpha, g sigma beta minus g rho beta, g alpha sigma alpha times n rho k prime sigma gradient alpha k prime beta. Okay, but I claim there's a minus sign. Now I think this minus sign comes from the fact that epsilon upper and epsilon lower in a Lorentzian signature spacetime are opposite in sign. That means if epsilon lower 0, 1, 2, 3 is plus, then the constant part, never mind root g, then epsilon upper 0, 1, 2, 3 is minus. I think that's where the minus sign comes, but you're free to check it for yourself. So when we contract these things, we end up with -2 n alpha k beta prime gradient alpha k prime beta minus the reverse contraction like this. Okay. Now we use what we've used many times before, this quantity and minus of this quantity along with that sign are the same because of these are killing vectors. So I can keep either of these two terms and just double it. Okay, so I'm going to keep the second term, which has a minus here and another minus here. So, and double it. So I'll get for n alpha k prime beta del beta k prime alpha. Okay. So this is epsilon mu nu a mu nu. And now I can easily evaluate this because this part is the left side of the geodesic equation for k prime. And the answer is kappa times k prime alpha. Now k prime is contracted with this n, and k prime dot n was chosen to be -1. So there's a minus. So we've got minus for kappa. Okay. And just to remind you, what is minus for kappa? It's this guy. So, and this is almost what we wanted. We wanted half of it, and that was the quantity A. And in that case, once we had A, then our integral is the integral of A times epsilon mu. Okay. So at this stage, we can say that so therefore A is equal to minus 2 kappa. And now the integral, but now notice that this is constant. Why is it constant? Because we proved constancy of surface gravity. Otherwise, it wouldn't be. It's such a beautiful subject here. Now we are supposed to take integral of A, excuse me. Yeah. Now we're supposed to take integral of A epsilon mu nu over the horizon. And A being constant comes out. We integrate epsilon mu nu over the horizon, but epsilon mu nu is the volume form of the horizon. And we've got minus 2k kappa A, exactly what we claimed. Very good. So now if we put everything together, we end up with the formula that the Komar mass is first of all a bulk term integrated over sigma T prime mu nu. And then, so this n is, by the way, the time-like forward, future-directed normal to the Cauchy surface. It's just a unit vector, just in order to write this invariantly. And then there's one contribution from omega and j. Let's go back and find it. So just to tell you that I didn't cheat. And that is here. So now notice that here, the contribution was 16 pi j, okay? And it was on the right side of mk. And I want to multiply it by minus 1 over 8 pi. This quantity here is only this thing. I ignored the normalization. So here to this, I have to multiply minus 1 over 8 pi g. So I get 2. So 2 omega j. Okay. So one of my terms is 2 omega j. What's the other term? In the other term, I integrated this guy, the null guy, and then I had to again multiply by minus 1 over 8 pi g. So in both terms, I had to do that, but I have to multiply, therefore, minus 1 over 8 pi g into that thing. And so I get plus kappa A over 4 pi. And this is a very beautiful formula that goes by the name of Smarr formula. Okay. Now let's stare at this formula. Is it the first law of thermodynamics? Absolutely not, because it's not a formula for the variation of anything. Secondly, at this stage, we wouldn't know what to do with this first term. It's a bulk term, and it depends on the bulk stress tensor. But what we want to know from the thermodynamic point of view is that if some matter has gone into the black hole, and at late times, there's nothing left outside, it's all gone in, then what does the black hole do? How does its mass change? That's the law. Okay. So at late times, we can assume that T prime has gone to 0, and we are back in the vacuum. I think there's a technical name for this assumption. And so we get what you might call the vacuum Smarr formula, mk equals 2 omega j plus kappa a over 4 pi, and we'll work with this. Now you may object that is there no contribution from the electric charge? Well, if we have vacuum outside, then by definition, then there's no radiation field, electromagnetic radiation. So obviously there can't be a Q. So an exercise which you may try, I haven't done it, is to put over here the stress tensor of the electromagnetic field, and then hopefully you get the Q term in the Smarr formula. It turns out that the Q term is actually phi Q, and it's interesting because this doesn't come with a factor of 2, while both of these you can recognize as double of the term that you would have got in the thermodynamic relation. Of course, this is not the thermodynamic relation, and it doesn't easily become that because it's not enough to vary J and A. If I want to vary M now, I have to also vary omega and K. I'm basically varying all the parameters. Okay, so this formula does not easily give you the thermodynamic relation. In fact, what it does give you is the following. So let me again go back to ignoring Q. I'll be satisfied to get the first law without Q. So delta mk is 2 delta omega j plus 2 omega delta j plus delta kappa a by, so there's a g here, 4 pi g plus kappa delta a over 4 pi g. And if you focus only on this part, it looks exactly like what the second law should have been for delta m, but double, because there's a 2 here and this is 4 instead of 8. But then there are these terms, and how are we to calculate these terms? Well, in quite a heroic work, Wald has calculated these terms and shown that their contribution exactly reduces this whole thing by removing these terms and replacing this 2 by a 1 and this by an 8. But it's rather a tedious calculation, and I don't want to do it that way. Okay, so we're not going to do this thing at all. We'll just avoid doing this. Okay, so let me actually erase it and find a clever trick. And the clever trick is due to Gibbons, and this is the last thing I'll do now, and so let's do dimensional analysis. And this sort of analysis can be helpful in many contexts in this subject. And the way we do it is we set C equals 1, and we also now temporarily set the gravitational constant equals 1. We can put it back at the end. And a very nice thing happens in that situation, which is that all units basically reduce to mass units. Okay, because this C equals 1, everybody knows, tells me that length units are equal to time units. I can measure length in seconds, or I can measure time in meters by using C equals 1. What does G equals 1 tell us? Well, for that, we should look at the dimensions of G. The dimensions of G are length cubed over mass times time squared. If you can just do this by putting it into Newton's gravitational law, this is the gravitational constant, and these are its dimensions. And because C is 1, we can cancel L with T, and we get L by M. And now we are putting this to be 1. Therefore, the dimension of mass is equal to the dimension of length. Okay, so far so good. So mass, length, and time all have the same dimension when G and C are 1. I don't know if you realized this before. I don't know if I realized it before, but it's quite a cute result. Okay. Now, what about area? What's the dimension of area? Well, it's length squared, obviously. So it's also mass squared. What's the dimension of angular momentum? These boxes, by now you figured out, means dimension, just scaling dimension, the dimension, the units. So what are the dimensions of J? Well, J has angular momentum starts its life having dimension m L cubed over t squared. Okay, as you can easily calculate. And again, because C is 1, L squared and T squared cancel. So this is ml. But since m and L are the same, this is also m squared. So both area and J have dimension of m squared. Now, there is a black hole uniqueness theorem. It goes by name of no hair theorem or whatever. Um, Again, it's a conjecture or theorem. It depends what you assume. But it basically says that the mass of a black hole, well, it says more, but it says in particular that the mass of a black hole with a given area, a given angular momentum, and in principle a given q only depends on these three quantities, and there are no other quantities which can decide the mass of the object. Okay, it just depends on these. But now okay, and Q is not there in our problem, so it only depends on A and J. Okay, now let's go back to the Smarr formula. The Smarr formula is this one. I'm again going to delete the charge part, so I'm not going to actually prove that part. And let's take this one and box it. Okay, so what is the dependence? Mk has a linear dependence on J here, but also has some dependence here. Likewise, this term has a linear dependence on A here, but we'll have some dependence on A and J from that. So these two we don't know for a general black hole, for a general spacetime. Okay. But the scaling argument says that after the dust settles, after I insert the values of omega and kappa in a given solution, the whole thing on the right has to be dimensionally a function of j and k of degree half. Has to be a homogeneous function of degree half. So because of this, M equals MAJ, where this is a homogeneous, this is the consequence of dimensional analysis, function of degree half, so that it can match in dimension with the left side. Okay. Well, when you have a homogeneous function, M of A and J of any degree, then there's a famous theorem, I think it's called Euler's theorem on homogeneous functions. I'm sure you have seen it, which says A del M by del A plus J del M by del J is equal to half of M. Here you basically put the degree, whatever it is, and here it's half. Okay. So half M, and now we can finally use the Smarr formula because we know M, this M is the one given by Smarr formula, and that answer is kappa A over 8 pi plus omega dot J. Okay, the 2's have gone. And now this tells me, now I can rewrite this equation as A del M by del A minus kappa by 8 pi plus J del M by del J. Sometimes I write the vector sign, sometimes I forget. It doesn't matter much. This is equal to 0. You can put a vector sign here also. Okay. And from this it follows, now A and J are independent variables. I can vary them independently. Therefore, these constants, these coefficients must be independently 0. So del M by del A is kappa by 8 pi. Del M by del J is omega. And therefore, dm is kappa dA by 8 pi plus omega dot dj, and we have the first law. I'll admit that it's a bit of a cheat because it used dimensional analysis, and I'm pretty sure that the answer became, the direction became clear when looking at the Smarr formula, because, right, why does it look so much like the first law, but it's not, because these are not infinitesimals, and yet it's like double of the quantity we expect to get. Well, one way is to calculate all this horrible thing which I wrote earlier, where you vary every term and then calculate all four terms. But a simpler way is just to use dimensional analysis. Okay. Now, there's another version of the derivation, which is called the physical process derivation, which also Ward apparently played an important role in, and I'm not going to do that. But it basically, instead, here what we have done is simply varied the parameters A and J and assumed that the solution settles down to some stationary solution. In the physical process, we actually imagine a black hole and imagine throwing in some matter, but we treat that matter as being light enough that it doesn't back react on the black hole. And then we look at the change in the black hole mass and we get the same formula. And if we throw in charged matter, we'll also get the charge contribution to this form. Good. So that's all I have to say. And we end here. Questions? Dim J is ml squared over t apparently. Why didn't you interrupt me to say that? Doesn't seem to affect my answer. Maybe that's true. Yeah, maybe that's true actually. Sorry. You're quite right. Thank you. Sometimes I write dimensions assuming things are already set to one, like, yeah, C or whatever. So of course, what I wrote and what you said are the same. Yeah, obviously this is correct because this is literally the angular momentum, R cross P, which is what it should be. Yeah. So P is ml by T, and then we cross it with another L to get R cross P. And this is the rest of it is still true. Good. Thank you for that. Any more questions, comments? Yes, Vinayak.
No, I'm fine.
Okay. Okay, then I'm going to stop the recording.